This is one of two videos meant to help you illustrate the two approaches to hypothesis tests. The first approach is called the critical value approach, shown in another video, and in this video I'll show you the p-value approach. In the critical value approach, you compare a critical value from the z or the t distribution to a test statistic, which is a calculated value of t or z. And in the p-value approach, you compare alpha, or your significance level. It's a percentage or a decimal, usually between 0.01, maybe 0.05 or 0.10. And you'll compare that to an area that is either greater or less than alpha. This video is intended for students who have already pretty well understood the calculations needed for hypothesis tests. That is, to calculate sample means and standard errors, to calculate z statistics or t statistics, and also to calculate areas underneath these z or t distribution curves. The video is only intended to bring all those concepts together into one picture to show you what a hypothesis test is doing. Now, in our example here, we've got a null hypothesis that the true population mean, or mu, is equal to 60. The alternative hypothesis then is that it's not equal to 60, which is two-tailed. The true mean could be much bigger than 60 or smaller than 60. And for no particular reason, I've chosen alpha equal to 0.05 or 5%. The other common values are 1% or sometimes 10%. Now, in this example, I have shown no information from your sample, such as the sample mean or a standard deviation, to show you that you can set up this picture in the rejection regions without knowing anything about your actual data. Now, in the p-value approach with a two-tailed hypothesis, we simply take the value of alpha, split it in half because we have two tails, and we say that we will reject the null hypothesis if something interesting happens in this lower tail or something happens in this upper tail where the combined areas of those rejection regions adds up to alpha, or our significance level of 0.05. So we have a rejection zone down here that is 2.5%, a rejection zone over here that is 2.5%, for a combined area of 5%. Now, when we collect our data, suppose we get a sample mean of 56.5. Suppose we get, either because we know the population standard deviation or we use the sample standard deviation to estimate it, we get a standard error of the mean of exactly 2. That means that our sample mean of x bar, if the null hypothesis of 60 is true, our sample mean of 56.5 is 1.75 standard errors below 60. This 1.75, or technically negative 1.75, is a z statistic or a t statistic. Now, the question that we want to ask is, while this value of 56.5 was below what we expected if the null hypothesis is true, sometimes sample means that are below the true value happen. How often? Well, we could take this t or z statistic, which is a value from the t distribution or the z distribution, and calculate the probability of getting values like negative 1.75. From the z distribution, you go directly to your table and look up negative 1.75, or actually you look up positive 1.75, and then you have to do a little bit of calculating. From a t-table, you can estimate it by trying to find the value that is the closest to 1.75, and then you find the areas associated with that. You can also calculate these areas directly in Excel using either a norm dist or a norm inverse function, or there's a t-dist or a t-inverse function. Now, suppose we calculate the area beyond 1.75, that is in the tail, to be, say, 4%. That would be illustrated like this. So the area beyond negative 1.75 in this tail is 4%. And that also means that the area above positive 1.75 up here is also 4% because these distributions are symmetric. Our p-value then is the area of these two red regions beyond 1.75. This is 4%. The upper tail over here is 4%. So our p-value is 4% times 2, or 0.08. And we say that values like 1.75 or more extreme happen 8% of the time. Because our significance level was alpha equals 0.05, this means that we're only considering rare things to be the rarest 5%. Our value, or our test statistic of 1.75, defines the rarest 8%. So while our x bar of 56.5 was smaller than we expected, it's not so unexpected or so rare to say that the null hypothesis is conclusively wrong. We would fail to reject the null hypothesis, and if somebody wanted to try to believe that the true mean is equal to 60, we would have insufficient evidence to say that that claim is wrong. Now, next up is the same procedure for a one-tailed test. So suppose our null hypothesis is that the mean is 60 or something greater. We would reject that null hypothesis if we get something that is not just less than 60, but significantly less than 60. Or if we find a value of x bar that is not just rare or unlikely to be below 60, but significantly or extremely rare and below 60. How rare? Well, rarer than 5%, our chosen significant level of alpha equals 0.05. Again, we can draw the rejection zone without any information about the sample itself. So if we set alpha equals 0.05, you simply draw a tail. Notice that this is one-tailed. Think about that alternative hypothesis again. To reject the null, you have to get not just a smaller value than what you expected, but significantly smaller. In fact, the 5% of the smallest values. So you draw your rejection zone as the smallest 5%, or a tail that has an area of 0.05. Now we use the same sample that we had in the two-tailed example. Suppose we get a sample mean of 56.5, a standard error of exactly 2. So that 56.5 is 1.75 standard errors below the claim. The question again is, how unlikely is it to get values like 1.75, or technically negative 1.75? Well, you calculate the area below negative 1.75, or the probability that a randomly selected test statistic, either a z or a t value, is below negative 1.75. That area was perhaps 4%. So we label it like this. The red area below negative 1.75 is 0.04. And we say that values like negative 1.74 or 75 or 1.75 standard errors below the mean happen about 4% of the time. For our definition of rare, of alpha equals 0.05, this is considered more rare, or less likely, 4% versus 5%, less likely than we're willing to tolerate. So we now have conclusive evidence that a mean of greater than or equal to 60 is probably not true, and we would say that according to our sample, we can reject that null hypothesis and say that the mean is much more likely to be less than 60. Either that, or we just observed a sample that should only happen 0.04 of the time, or 4% of the time.